Hi folks, and thanks for joining me. You're looking at the loudspeaker impedance meter that I did a little small video on, just an intro, a few weeks back, and it leverages Arduino, and I'm using a Arduino Uno, as you can see there, and I just took a couple pieces of acrylic, cut that, and made me like a little small display piece here for it, nothing fancy. And you can see I've got my iPhone using SGenerator and generating a tone at 1000 Hertz, right at 1 volt peak to peak is my design. And you can see I have a 10 ohm resistor here across my terminal, and I'm reading the DC resistance here. And of course I've got a loudspeaker here that I'll hook up in just a moment, but just wanted to show the unit here working. We'll hook it up here. For those that have headphones, earbuds, or whatever, just take note. I'm going to generate a 1000 Hertz tone. One thing you'll notice on the LCD screen, I've got my impedance showing open. That's just part of the Arduino code or the sketch, and I've done that just to indicate an open voice coil. Of course we would be able to hear that depending on what frequency we're generating a signal. In addition, if I have no signal being driven to the device here or at these two locations using the signal generator, it indicates open as well. So here we go, and there's the tone I was referring to, 1000 Hertz, 1 volt peak to peak, and again I'm calibrated right at 10 ohms, so I found the accuracy to be fairly good compared to my DATs, which I'll build on in just a moment. So you can see here I've got a delay in my code, but you can see the sample rate here. It updates I think often enough. Let me just turn that off there, and you can see it go back to open. Or I can do this, and you'll see it open as well with no speaker attached. Let me pull up the schematic here of the little adder board that I had to build. If that's showing up here on camera, you may be able to see it down in there. There's a couple different boards. There's a voltage reference board that we'll speak to, and a rectifier circuit to take the AC voltage back down to DC. Apply Ohm's Law and calculate the impedance of the speaker itself. Let's reference the sketch real quick, just the top half of the sketch, and just a couple of my notes and disclaimers. Hey, look here at the sketch for the loudspeaker impedance meter. You can see I'm measuring the impedance using Ohm's Law. So we're only measuring the loudspeaker resistive impedance. The reactive components, of course, are not measured in this design. So to get the impedance, of course, I'm just taking the voltage divided by current, as you can see here. It'll really be helpful for those troubleshooting or want to do a sweep of a speaker, again out of circuit, using my iPhone with SGenerator there sweeping 20 to 20,000 Hertz. You can see the accuracy there is compared to DATs, so not bad. And I should have noted that's probably plus or minus 0.06 ohms. Again, you can use an external audio oscillator as well to drive the design. I have my unit calibrated at 1 kilohertz, 1000 Hertz, using a sine wave. Of course, if that amplitude varies from that, the code itself or some modifications would have to be made to ensure the accuracy of the measured results. Couple disclaimers: if you're going to use your smartphone to drive the circuit, you're doing so at your own risk. Keep that in mind. I had already alluded to the audio carrier level will influence the results as well. And I'm using a precision half-wave rectifier. It's powered from 9 volts. So my reference is external, set at 2.048, and that's just to improve the accuracy of the results. We'll come back to the code here just in a moment. Again, I'm not an expert on code, so for those out there that review the code or use it, just tweak it or use it as a foundation. Let's take a detailed look here at the circuit. So here's a look at the circuit itself. You guys know your conventional diodes, they just don't work. They won't conduct until the knee voltage is exceeded. In this case, 300 millivolts for my design there for D1. So no rectification takes place since I'm dealing with low AC voltages. At 1 volt peak to peak, you can see I'm utilizing an op amp there as a half-wave rectifier, and it's connected as a non-inverting amp. And you'll notice diode D1 there. That's my feedback is through that device, and the way it works, of course, is a non-inverting AC voltage comes in from my signal generator that goes positive. The output is driven to the 300 millivolt knee voltage. Now as the AC voltage input from my signal generator goes negative, the negative output positions D1 to be reverse biased. So it acts as a voltage divider with resistor R1. So the circuit itself, you'll see, just follows the positive input signal, thus muting or rejecting the negative ones, and that creates the half-wave rectification. Now focusing on the iPhone itself, acting as the signal generator. Using SGenerator there, you'll see the signal itself comes out, goes across resistor R3 in my design, which is a 10 ohm resistor. So you'll see all I'm doing is measuring the AC voltage at both sides of R3 and applying Ohm's Law. So what I'm doing to get current is looking at A1 minus A0, divide that by 10 ohms, gives me the current, and then I can take the AO voltage, divide that by the current, and calculate Z, or impedance. So that's basically pretty straightforward how the circuit works. You'll see the connections here that are forthcoming that go back to the LCD module, and let me touch on the LM4040 as well. Before moving forward, I wanted to touch base on diodes D2. Again, they're Zener diodes, and they're reverse biased. The purpose of those diodes, again, is to provide protection to the Uno and just make sure that we do not exceed 5 volts DC to analog ports A0 and A1. So back to the LM4040. I'm not a SME on this subject, but I had read numerous articles on the web, a bunch of smart folks that mention using the LM4040 just because it's a static reference voltage, unlike the internal voltage that seems to fluctuate around. In my case, I noticed anywhere from 4.8 to about 5.1 volts. So that creates a lot of fluctuation on the calculated results. So the LM4040, you can see the way it's connected there is an external reference voltage, and when you review the code itself, you'll notice the code is modified accordingly, and I'm calling out the external reference as well, just to keep the results of the output as accurate as possible. For those that followed the introduction video, you'll notice the breadboard design leveraged an LM324. A little bit different design on the rectifier, the half-wave rectifier circuit. Not as clean as my final design that I just shared the schematic on. However, the 324 would work in place of the 6482 using the same layout. The 324, of course, has more op amps integrated, and the LMC 6482 has the 2 op amps integrated into one unit, single rail supply, so that worked out really well. Let's take a look real quick at the sketch at a high level, and then we'll demonstrate the unit here doing some sweep tests as well using HyperTerminal. I'll take those readings and dump those into Excel, and I'll share a few charts that I created, and I'll make all these documents available for download in addition to the sketch as well. As I alluded to earlier, I'm not proficient in writing code, so you guys just take this as a starting point. You can see I'm taking 250 analog samples, and I'm keeping count of the results for the voltages that I receive for analog pins A0 and A1 for those 250 samples, divided by the 250 samples to get a average voltage. And I've noticed, of course, more samples, it seems that gives you a better average, and it kind of slows down the fluctuation that you see on the output itself. You can see I tried to put comments to the right of the code so you guys can see what's going on and how I'm doing the math there for the calculations. There's the analog reference that I mentioned as well, the external pin. That's where I've defined the VCC2 output for pin number 13 to drive the LM4040 there as well. Here you can see I'm calling out my LCD and serial communications as well. And again, my number of samples, you can see there some AO analog read. That says 100 samples. Again, you could define that. In my case, that's 250. I should have updated that in the code. With 250 analog samples, I found a delay of 2 milliseconds seemed to work best. That way the LCD screen's not jumping around and going crazy on you. You could modify that accordingly. And as I mentioned too, just below the delay there of 2, you'll notice that's where I've made a reference there of using the LM4040 external voltage reference there to improve the accuracy. So the math itself there, which I mentioned just a bit ago how I'm doing it, also references the 2.048 volts versus your typical 5 volts or whatever your actual measured voltage would be. And you can see below that how the current is calculated. And you'll notice there's a correction factor in there that I have just because of the resistance value is not precise at 10 ohms. So in this case, I've got an adder of 0.45 that can be modified during the calibration process, which I'll demonstrate here in just a bit by using some known 10 ohm or 5 ohm resistors. And the remaining code is straightforward there. Now, taking a look here at some of the charts that I created just by dumping the data there that I was able to capture into Excel and chart these out to be able to look at the response of an 8 ohm speaker from 20 hertz to 20,000 hertz. And I compared that against my DATs, and you'll see the results are almost spot on. A little bit of variance, which is to be expected. But overall, I think the results are satisfactory and good enough, just for a hobbyist or just playing around, in the sweep mode versus a fixed static test, say at 1000 hertz. I had mentioned the calibration process. Again, part of that is in the line of code I put in, that 0.45. I think I ended up at 0.5 adder versus the 0.45 that I shared. You can see here I've got the iPhone with SGenerator running, and I've confirmed my output is 1 volt peak to peak, and I'll just hit play. And again, the way I have my terminals configured, this is my external signal generator reference point as well, where I can hook up here between the red and black. And I'm going to just place a 10 ohm resistor here, and you can see it locks in very close to 10 ohms, so that's what I'm looking for. And I've done the same here by adding another 10 ohm resistor. Let's see if I've got one here in parallel. I think this is 10 ohm, we'll find out. And you can see we're back at 4.919 ohms. So very close, and I've checked the resistance there on my meter, and that's very, very close there. I keep fluctuating back and forth between 4.9 and some change back to 5 ohms. And if I go here and we put this in series, see if I can get these two together here. You can see we're at 20.2 ohms. So relatively close there with the math. And again, I can tweak that, using the code itself in the sketch that's provided. So that's kind of the calibration process after everything is put together. These are 1% resistors, and I just checked them against two different meters, my Fluke and my LCR meter. So hopefully that was helpful as well. Again, if there's no signal present at this terminal, you can see the way I've got the sketch written there to add open to the impedance. Let me hook the speaker back up for those watching and listening. Just keep in mind I'm going to generate a 1000 hertz tone, so you may want to adjust your volume accordingly. And you can see there we're measuring the impedance of the speaker here real time. And I'll show you guys something here, that how the impedance changes, of course. You put my hand over the speaker, and you can see how the impedance itself changes just by me kind of muffling the sound itself coming out of the speaker, how the impedance itself is impacted versus DC resistance. So the enclosure itself versus free air does make a difference. I mentioned the drive levels do make a difference. I'll show you. Let me turn this down, and again I'm calibrated to 1 volt peak to peak. But you can see if I adjust the amplitude down, the impedance drops. Alright, let's shut that down, and let me show you the sweep mode as well. We'll go here. I've got a preset sweep at 1 volt peak to peak. We'll load that up. And again, for those with earbuds, headphones, just take note here. I'm going to generate a tone starting at 20 hertz. And you guys can see that and hear it. And I can adjust the duration of the sweep. I'll go ahead and turn this off for now, let you guys get the gist of that. So I can increase the number of samples by modifying the code and change my delay from 2 milliseconds to 1, or I can go in here and just change 360 seconds or so, just to make my output more granular if I'm looking for a particular problem at a certain frequency. So folks, I hope you found this helpful. Again, it's a simple and easy circuit to build. Let me disconnect this and I'll just show it to you guys here. I went around building it here. I just wanted it to be kind of cool looking here, so I just took some acrylic pieces, cut it, drilled it off, made some standoffs there with some screws, fasteners, put some rubber feet on the bottom, as you can see. And there's my board that I built that has the half-wave rectifier and the diodes and the few resistors there that are called out on the schematic. So a very simple and easy circuit to build, and you can have up and running, put in a better enclosure in no time. Thanks again for watching, folks.